Hello, everyone. My name is Tohid Shekari, and I'm currently a senior research engineer in Georgia Tech. Today, I'm going to present you our latest paper, which is entitled MAD IoT 2, Modern High-Wattage IoT Botnet Attacks and Defenses. This is a joint work between Georgia Tech and the University of California in Santa Cruz. So without further ado, let's jump into the presentation. The first thing that I would like to start with my presentation is the term manipulation of demand IoT or MAD IoT. So what is exactly MAD IoT? The term has been introduced for the first time in USENIX Security 2018. And the term refers to an attacker who has access to a high-wattage IoT botnet and is trying to take down or cause blackout in a power grid. So high-wattage IoT devices such as electric vehicle chargers, electric heaters, HVAC devices, or air purifiers can be compromised and controlled remotely by attackers. And an attacker who has access to a large number of such IoT bots, they can turn them on or off simultaneously from random locations to cause technical issues in the power grid, which can eventually lead to frequency instability, voltage instability, and line overload to cause a widespread blackout in the entire system. So here in this presentation, I will talk about the bulk power grid. If we model the power grid with different nodes and edges like a graph, each node represents a very big city or a power plant, and each node represents the transmission lines that are connecting everything together. So we know that large IoT botnets can be employed by attackers to attack the power grid to take them down. But 1 year later, another set of authors came in and presented another paper in USENIX Security 2019. The title of the paper was "Not Everything is Dark and Gloomy." And the second paper basically argued that it is not as easy as it was claimed in the first paper to take down the power grid with these IoT botnets because of the existing protection schemes and the grid controllers that the previous authors just overlooked in their simulations. So if you launch the attack randomly from different locations or from different nodes, it's not going to be as effective as it was claimed. And it will have very low and trivial success rates, such as 1%. So studying these two papers, we started to also take a look at the recent natural blackouts that are happening around the world. According to our analysis, we noticed that the current protection and control schemes are able to control most of the faults in the grid if there's any technical fault, but these technical faults are happening in random locations. But by coincidence, if these natural events happen in the weak nodes or weak locations of the power grid, it can cause to the blackout. And this coincidence is happening quite rarely because, let's say, the operation of the grid is changing 24/7, and then the critical nodes of the system are changing 24/7 as well. But by any chance, if a random event happens in the critical node, it leads to the blackout. So looking at this phenomenon, we were thinking, can we mimic a similar situation where we can cause blackout in the grid by the help of this IoT botnets? And the answer to this question is yes, we can. So we can attack on random nodes. So instead of attacking the random nodes that was proposed by the previous attacks, we claim to attack the system from the weakest nodes of the grid. And changing the loads in specific nodes is been proven to be more catastrophic because we're attacking the weakest nodes as similar to the historical blackout. So we can cause instabilities such as frequency and voltage instabilities. But in order for this to happen, we need more detailed information about the grid operation because it is changing 24/7. And also we need to have access to a distributed high wattage IoT botnet. It needs to be distributed among all the nodes or all the geographical locations in the grid. So that whenever we say we want to change the system demand in New York or California, we should be able to do that. So based on these explanations, the MAD IoT 2 version 2 is expected or is executed in two stages. Stage 1, where we acquire the required data for launching this attack, such as graph of the grid, which can be obtained offline, the transmission line parameters, and the real-time system operation data, meaning the power consumption and generation at different nodes in real time. And in the stage 2, which is the system analysis stage, and this is being done periodically every 5 to 15 minutes, we find the weakest nodes of the system from the stability perspective, and we launch the attack from those weak nodes. So how we can obtain the graph of the grid and line data? This can be done by reconnaissance, basically, because everything that is doomed to be basic or consistent with security by obscurity, it cannot be protected for a long time. In addition to this, we could do offline analysis by using some semi-automated ways, such as using the satellite pictures, because the transmission lines of the power grid and also the power plants, the cities, everything from the bulk power grid perspective is so big that you cannot hide them. So if you have access to a satellite picture, you can write your own image processing or computer vision algorithm to extract the graph of the grid. And the right side figure in this slide shows an example open source tool that the researchers developed to obtain the graph of the Peru or Chilean power grid structure. For the real-time system operation, the power grid operation data, we need to get access to those data. And by the system nodes, again, we mean the cities or big power plants, these kind of things. So these kind of information can be obtained from the independent system operators website or from a tool called Bloomberg Terminal. And we can write our own crawlers to obtain such data, which we did in our research. For example, if we're targeting the New York power grid, you can just Google New York ISO. You can log into their system, not logging, just navigate to their website, and then look at the real-time power generation and consumption at different regions of their system. So in the second stage, we obtain the necessary information, and now we want to determine the weakest nodes of the power grid to launch the attack. So we can do the mathematical calculations to rank the system nodes based on the stability perspective. It is very hard to calculate it in real time because it has very high dimensional nonlinear equations. So from the literature, we use two indices that have the approximation methods, index 1 and index 2, to find the weakest nodes. For the numerical evaluations, we cannot do the real world implementation because it has devastating effects. So we have only simulations, and we simulated two test power grids, IEEE 9 node and 39 nodes. And we comprehensively model the system, its controllers, and its protective schemes so that we have the complete model of the system according to the first and second paper that we analyzed at the beginning of the presentation. So the overall performance of the attacks, here we compared the proposed attack with index 2, the proposed attack with index 1, the second paper and the first paper that we analyzed, and the top figure shows the results for the IEEE 39 node system. The below figure shows the results for the IEEE 9 node system. And if we have the precision, we call an F1 score, and the success rate of the attack can be presented in the best way by the F1 score. As we can see in both figures, the F1 score of the proposed attack, especially index 2, is much higher than the first and second attack that we presented at the beginning of the presentation. So we know that right now, the new attack, MAD IoT 2, is effective, but what we can do to defend against that? So we have some countermeasures. We have data-driven countermeasures or long-term. As you remember, the main reason that we could cause the blackout is that the data privacy issue, the data is available to the attacker, the real-time power grid operation. So if we limit access to this data, we might be able to protect against that. We can release the delayed version of the grid operation data, and we've proved that 1% parameter estimation error reduced the F1 score by almost 5%. We could also register the high-wattage IoT devices in an online database to basically monitor the bulk behavior of them to protect against any such attacks. There's also hardware-driven attacks. So with revisiting the existing protection schemes, we can significantly reduce the success rate of the attack. So as far as of the conclusions, we introduced an attack that the targeted high-wattage IoT botnet can cause power grid blackouts. MAD IoT 2 targets the weakest nodes of the grid. We have presented short-term and long-term countermeasures, and also the attack vector can be studied in other domains, such as the electricity markets for future studies. Thank you for listening to our presentation, and I will hear for your questions. Thank you.